depends on the rental rate, right? So this is the capital per person, and we are assuming labor to be unity, right? Now, capital R is R plus small r plus delta. We have obtained that before. Uh, so once the interest rate and the wage rate are determined, small y is a linear function of k, right? It's a linear function with intercept of w and a slope of r, right? So r can take different values. This is this is the function. This is basically your income per worker. This is this income per worker when we are looking at a rental rate R0, capital K0, wage W naught, and this is when it has changed. The slope. Here we are looking at a flatter slope. So the idea is that each of these lines which are tangent. So these are two different income functions. These are like the income per workers. These are two different income per worker schedules for two different initial capital stocks. So one, this line which is tangent to the production function at a certain value of capital, this is basically for, this is the function for capital level K0. And this is the same for a higher value of capital per worker, which is K1, right? So the idea is that the interest rate and the wage rate are determined. Y is a linear function of K with intercept of W and slope R. Okay. Now, of course, R, that is capital R, depends on K through the marginal productivity condition, right? So let's refer to the marginal productivity condition. You should always keep in mind that in a perfectly competitive setup, this would hold true, right? So f prime k would be equal to capital R. F prime k is equal to small r plus delta, which is equal to capital R, right? So of course, capital R depends on k. So R plus delta is capital R, that's the rental rate, and it's a linear function of k, so right? So it depends. There's a one-to-one correspondence between capital per worker and rental rate because of this condition always holding true, right? So R is the slope of the income function, right? So this is our income function. This is our income function, slope of which is capital R, and R, this must be equal to the slope of fk at the specified value of k. So for example, let's, looking into this figure, see, take any value of any specified value of capital k naught, let's say. So the R, which is the slope of the income function, that must be equal to the slope of fk. This is fk, and this slope of fk must be equal to the slope of the income function also, provided we are talking about k naught value of capital. So I repeat, capital R, which is the slope of the income function, this particular income function is actually R1, so R1, which is the slope of this income function, this must be equal to the slope of fk, which is this curve, for the specified value of capital, which is k naught. So we are considering the tangency point here, right? So at this point of tangency, the slope of the income function, the slope of the income function should be equal to the slope of the production function. Okay, so similarly, if we move to a different point, if we move to a higher value of capital, the same should hold true, right? So the idea is that R depends on K through the marginal productivity condition, which is F prime K equal to capital R, which is equal to small r plus delta. So the slope of the income function must be equal to the slope of Fk at the specified value of K. So see at K naught, what's happening? The slope of the income function, which is R naught, this should be equal to the slope of the production function at K naught. At this point, what is happening? The slope of the income function, which is R1, this should be equal to the slope of the production function at capital equal to K1, right? All right, so now this particular figure shows two values, K0 and K1. Now the income functions at these two values, K0 and K1, are given by straight lines, as you can see, that are tangent to Fk at K0 and K1, right? This is one point of tangency, this is the other point of tangency, right? So this particular figure shows two values of capital K0 and K1 respectively, and the income functions at these two values are given by straight lines, these straight lines which are tangent to Fk at K0 and K1 respectively. So as K rises during the transition, so from K0 to K1, as K increases, the figure shows that the slope of the tangent straight line declines from R0 to R1. So at K0, what is the slope of the tangent straight line? The slope of the tangent straight line is R0, right? And at K1, what is the slope of the tangent straight line? It is R1. So R1 definitely is flatter than R0. So what we are seeing is that as K increases during the transition, as K increases from K0 to K1, the slope of the tangent straight line falls. There's a decline in the slope of the tangent straight line. There's a decline in the slope from R0 to R1. So the slope of the income function becomes flatter as capital per worker increases from K0 to K1, right? So also from this figure, we can see that the intercept, which is W, small w, that actually increases as capital increases from K0 to K1. The intercept increases from W0 to W1, right? This is how the wage increases, right? Okay. Now, now that we have established the behavior of input prices during the transition, what we can do is we can actually use this idea to look into a few policy experiments, right? So just to give you an idea, suppose let us consider this figure. Let's consider this particular figure, 1.6 in Barrow-Martin. So what this depicts is, our good old-fashioned basic Solo-Swan equation. So we have a n plus delta schedule, we have an SFK schedule, SFK by K schedule, right? So suppose the economy is initially at a steady state position. So suppose economy is initially situated at a steady state with capital per person equal to K1 star, right? Now imagine that the saving rate increases permanently from S1 to, let's say, a higher value S2. Possibly because households change their behavior, or maybe the government introduces some policy that in turn raises saving rate. So for whatever reason, there's an increase in the saving rate from S1 to S2. Now, in terms of the figure, what would happen? How would the SFK schedule change if there's an increase in saving? So, of course, there would be a rightward, outward shift in the SFK schedule, right? So, in terms of this particular figure, what you would find is that the SFK by K schedule shifts to the right. There's a rightward shift in this particular schedule. So the intersection with the n plus delta line also shifts to the right. So this is the initial point of intersection, which gives the initial steady state K1 star, and as the saving rate increases, the new point of intersection gives you a new steady state value of capital purpose. So since the intersection with the n plus delta line shifts to the right, the new steady state capital stock K2 star exceeds K1 star. Now, how does the economy adjust from K1 star to K2 star? Now, at K equal to K1 star, the gap between the S1 Fk by K curve and the n plus delta line it's pretty obvious that there's a gap. There's a very conspicuous sort of gap between the n plus delta schedule and the SFK schedule, right? So, question is, how does the economy adjust from K1 star to K2 star? So at K equal to K1 star, the gap between the S1 Fk by K curve and the n plus delta line is positive. So saving is more than enough to generate an increase in K. Now, as K increases, the growth rate falls and it approaches zero. Slowly, see, there's no gap at all. It approaches zero as K approaches K2 star, right? So this particular result is showing that a permanent increase in the saving rate actually generates a temporary sort of positive per capita growth rate. It's a positive per capita growth rate, definitely, but it's a temporary positive growth rate. This growth rate is not permanent. The positive growth rate is not permanent, right? So in the long run, the level of K and Y are permanently higher, but the per capita growth rates very much return to zero. The level of capital per person, the level of output per person, those are higher in the long run as your saving rate increases. So if there's a permanent increase in saving rate, as we are noticing here, there's a permanent increase from S1 to S2. What that generates is a temporary increase in the growth rate. There's a temporary positive growth rate. However, slowly, as the economy inches towards the new steady state, K2 star, the positive growth rate keeps on falling until it reaches zero. What does happen, however, is that there's a permanent increase in the level values of the per capita variables, right? So in the long run, the levels of K and Y are permanently higher, but the per capita growth rates return to zero, right? So the positive transitional growth rates may suggest that the economy could grow forever by raising the saving rate over and over again. However, there is one problem with this line of reasoning, and that is the fact that the saving rate is a fraction, that is a number between 0 and 1. Since people cannot save more than everything, this saving rate is basically bounded by 1. So notice that even if people could save all their income, the saving curve would still cross the depreciation line, and whenever there's this intersection, so to say, as a result of that, the long run per capita growth would stop. So the reason is that the workings of diminishing returns to capital eventually bring the economy back to a zero growth steady state. So therefore, we can now answer the question that motivated the beginning of this chapter, that can income per capita grow forever by simply saving and investing in physical capital? So if the production function is neoclassical, the answer is no, it cannot, right? So we can now also assess permanent changes in growth rate of population N, or maybe some external change. So these changes could reflect shifts of household behavior or changes in government policies that might influence fertility. A decrease in N basically shifts the depreciation rate downwards, right? So this depreciation rate would shift downwards, and or rightwards, whichever way you like it. So the net result of that would be the steady state level of capital per person would be larger. However, the long run growth rate of capital per person would remain at 0, right? The long run growth rate of capital per person would very much remain at 0. That's the take home message from this particular lesson, that in the long run, these sort of changes, you can play around with the parameters as much as you like, but that is not going to provoke a permanent increase in the growth rate. Growth rate is eventually going to return to the 0, right? The 0% growth rate is going to be maintained, no matter how much you keep on, tinkering the parameters. So basically the thing is, whatever parameters we are noticing here in this particular figure, see all the different schedules, they deal with certain parameters, right? There's N, there's delta, saving rate, etc. Any changes in these parameters, these changes might reflect shifts in household behavior or changes in government policies, right? So any changes would lead to changes in the level of per capita variables. However, it's not going to provoke any change in the long run growth rate, because there might be a temporary increase or decrease in the growth rate, but eventually in the long run the growth rate is going to return to the 0% value, right? So the long run growth rate of capital per person would very much remain at 0. You need to have some other changes. You need to have changes in innovation, maybe, or because technology throughout this example we were not taking into account technological changes. Perhaps technological changes can lead to changes in long run growth. We'll look into that particular aspect later on. But the thing is, a permanent and once and for all sort of improvement in the level of technology has similar temporary effects on the per capita growth rates. If the production function Fk shifts upward in a proportional manner, So whenever, this FK, this takes into account, suppose this takes into account technology, this output is a function of capital and output is also dependent on total factor productivity, let's say. So if there's an improvement in technology, then production function shifts upward in a proportional manner. And the saving curve, this particular curve, as a result of that, as a result of an increase in FK, the saving curve is going to shift upwards, right? So, since the production function Fk shifts upward in a proportional manner, the saving curve shifts upward, and the K dot by K, which is the growth rate of capital, again becomes positive temporarily. So whenever there's, this is, suppose this is the initial position of the SFK by K schedule, and there's an increase, there's a temporary increase in, or a short run increase in savings rate, then immediately you would notice this gap between the schedule, this particular schedule, and the N plus delta schedule at this particular capital per worker, level of capital per worker, right? So K dot by K, or growth rate of capital, this becomes positive temporarily. So in the long run, the permanent improvement in technology generates higher levels of capital and output per person, but no changes in per capita growth rates, right? So the key difference between improvements in knowledge and increases in saving rate is that improvements in knowledge are not bounded, right? There's no limit to improvements in knowledge. That is, the production function can shift over and over again because in principle, there are no limits to human knowledge. The saving rate, however, is physically bounded by 1. It's a fraction, so it cannot go above 1. It cannot exceed 1. It follows that if we want to generate growth in long run per capita income and consumption within this particular neoclassical framework, growth must come from technological progress rather than from physical capital accumulation, right? So this is the bottom line. So if we are to work with a neoclassical production function, or a neoclassical sort of setup, then if our objective is to generate long run growth in per capita income and per capita consumption, then this type of growth must actually come from technological progress rather than physical capital accumulation, right? Because whenever we are talking about physical capital accumulation in this rather simplistic setup, that is happening through investment. So, whatever you are investing, that rather whatever you're saving is entirely getting channelized into investments, right? So if that is the case, then definitely there would be a temporary increase in the growth rate, but this would be a one-time increase, because this saving, the capital accumulation or investment, that is happening through saving and saving only, and there's a limit to saving, right? Your saving cannot exceed 1, it cannot go above 1, right? So at one point in time, the amount that you are channelizing into investment, that proportion of your income, it would get exhausted, and eventually you cannot save more and you cannot invest more. Hence, gradually, once you are not able to save more and your incremental investment stops, what you would notice is slowly this portion, this gap, slowly is going to reduce, and the growth in per capita capital is going to fall. It's going to keep on falling until it reaches zero. That is, this new point of intersection. So that's the bottom line, that if we want to generate growth growth in long run, basically long run per capita income and consumption within this particular neoclassical framework, then that sort of growth must be generated from technological progress rather than from accumulation of physical capital. So we have actually observed before that differences in government policies and institutions can amount to variations in the level of technology. For example, higher tax rates on capital income, failures to protect property rights, and also distorting government regulations. These can be economically equivalent to a poorer level of technology. However, it is probably infeasible to achieve perpetual growth through an unending sequence of improvements in government policies and institutions. So the idea is that, therefore, in the long run, sustained growth would still depend on technological progress. There's no alternative to technological progress, because all the other sort of options that we have, those options cannot be sustained over a prolonged period of time, right? So even though we are considering improvements in government policies and institutions, there cannot be an unending sequence of such improvements in policies and institutions, right? So you cannot achieve perpetual growth through such improvements in such policies, right? So in the long run, if you are thinking about achieving sustained growth, then you have to be heavily dependent on technological progress. And how this sort of technological progress can pave the way for long-run growth, we would be looking into that particular aspect in the course of the next few lectures. Okay, so any questions till now? So in the next class, we'll be looking into convergence, and after that, we'll be looking into the effect of technological progress on long-run growth. Okay, so we'll be picking up from here, from convergence in the next lecture. Okay, so all right, so I'll see you tomorrow. Thank you.